What way did you guys use? Did you use Pythagorean theorem or the identity?
I used identity.
Got one for the identity. Theorem? Theorem?
Identity.
Identity? Think you use theorem? Identity? Let's go, not the other 9 online. What you use?
Identity.
Thank you.
Theorem.
Theorem.
Both just in case.
So the majority of you guys use the theorem, okay? That is totally fine. You just want to make sure, just like you would if you were using the identity, is that you want to make sure you put the triangle in the correct quadrant that is in, okay? So then that way you know whether or not you need to label a particular side as a negative. Because if this happened to have been in the second quadrant instead, that adjacent side would have been what? It would have been negative, and that would have affected cosine and all the rest. Same thing with the identity. You want to make sure you know what quadrant you're in, because when you take the square root of both sides, you're always left with what when you take the square root in an equation? Plus or minus. And so then you would need the minus there if that was the case. All right, but we are in the first quadrant, so if I use Pythagorean theorem, that becomes 3 squared plus our unknown side squared is equal to 4 squared. Remember, the C is always the what in Pythagorean theorem?
Hypotenuse.
The hypotenuse. So that becomes 9 plus b squared is equal to 16. B squared is equal to 7. So b would be plus or minus the square root of 7, but we know specifically it's going to be positive, square root of 7. So cosine of x is equal to?
Square root 7.
You would get the exact same thing if you use the identity. This would have been 1 minus 9 over 16. This would have been 7 over 16. So then you'll have cosine squared x equals 7 over 16. Take the square root of 7 over 4 plus or minus, but we wanted the positive version. Sine 2x, you just plug it into the theorem that says 2 sine x, which I know is 3/4, times cosine x, which is 7/4. And you multiply straight across. What does that become? Always.
3 root 7 over 8.
3 root 7 over 8. Yes, always make sure you guys simplify your fractions. Cosine 2x. There are 3 different identities, and we actually know sine and cosine. So we can use any of them. But what if we got cosine wrong? Then we have no hope of getting cosine 2x correct. So always try to use the original value that they gave you, which was sine x, okay? What formula of cosine 2x has sine only in it?
1 minus 2 sine squared.
2 sine squared x, very good. So I'm going to replace sine x with 3/4. Order of operation says I need to do what? First, the power. So that becomes 9 over 16. This becomes 1 minus 18 over 16. And what's that final answer? -1/8. Wonderful. Last but not least, tangent 2x. Is there an identity for tangent 2x? Is there an identity for tangent 2x?
No, ma'am.
No. So how do I find tangent of 2x?
Take sine 2x and put it over cosine 2x.
Exactly. Don't forget that tangent is sine over cosine. So tangent 2x would be sine 2x over cosine 2x. I know that sine of 2x is 3 root 7 over 8. And I know that cosine 2x is negative 1 over 8. How do I simplify fractions divided by fractions? Keep, change, flip. So this is just going to give me a negative 3 root 7 for the tangent of 2x. Incorporating all of your identities that you need to know how to use for A&A SO. We continue to use these concepts and apply them here. If A is an obtuse angle in a triangle and sine A is equal to 5 over 13, calculate the value of sine 2A. Well, we know that sine 2A is that double angle identity. What's that double angle identity? Always want to make sure that if the problem gives it to me as some other different type of variable, please try to stay consistent and use that variable. Okay. So I need this identity here. I already know that sine A is 5/13. The only thing I need now is cosine. How can I find cosine A?
Pythagorean identity.
I use the Pythagorean identity. Just like how we did before. I am using the altered one just so that I can save some time from like that subtracting over of the sine squared A. Remember, it's the same thing as the original sine squared x plus cosine squared x is equal to 1. Sine is 5 over 13. Square that. 5 over 13 turns into You guys know them perfect squares. So when I do 1 minus 25 over 169, I need common denominator, so that's 169 over 169 minus 25 over 169. That turns into then I take the square root. What are you forgetting? And this one is definitely important, that plus or minus, because which one is it?
Don't you have to think about what's hard right now?
It's negative because it's obtuse and cosine would be to the left.
Exactly. It would be the negative. If you think about it inside of a coordinate plane.
Oh, it's an obtuse.
It has to be an obtuse angle, so that means that that terminal side and that initial side would fall into that second quadrant. So here's your obtuse angle. And so if we were to use Pythagorean theorem instead of the Pythagorean identity to do this, our right triangle would have been in the second quadrant. Hence, cosine would have been a negative value. That's how we create that obtuse angle that they told us about from the very beginning. So it wouldn't be positive, it would have to be negative because A is an obtuse angle. I probably should have labeled this A instead of theta. So multiplying straight across and reducing if I can. What's my answer? Well, 2 times 5 is? N times 12 is?
-120
Over?
169.
There we go. And that cannot reduce. This question actually was a question from like an old IB exam. Okay, what of course tripped up students was the fact that they forgot about the whole obtuse angle. It's going to put you in your second quadrant every time. Okay. Now, mentioned something about it before. We're going to see about this. Everyone, I want to see if you remember the unit circle. The unit circle is definitely something that you'll need to know for this unit, okay? Because especially when we get to solving equations such as this, and we're told to find the value of theta between 0 and pi, and giving our answers exactly, we are looking for corresponding values on the unit circle, so you need to know it. So if you did not do good reviewing the unit circle, then that needs to be a part of your studying things today, okay? So that way you can put that unit circle back into your mind. But we're going to solve this equation. 2 cosine squared theta plus sine theta is equal to 2 for theta in the interval 0 to pi. And of course, we're going to give our answers exactly. This is a non-calculator problem. It's very rare that a circular function problem is going to be on the calculator section unless you're looking at an application circular function problem. But something like this, a solving problem, it's very rare it's going to be on the calculator section. So 2 cosine squared theta plus sine theta is equal to 2. To refresh your memory, whenever you have mixed trig functions, one of the ways that you could solve this is to get it in terms of one trig function, right? Since you have a normal sine theta, you might want to see if you can turn that cosine squared theta in terms of sine theta. Is there a way we can do that? Is there a way I could rewrite cosine squared theta so that it's in terms of sine instead of cosine?
Could we use the Pythagorean identity?
The Pythagorean identity of 1 minus sine squared theta, yes. And by doing that, that puts the equation in terms of sine only. And from there, we'll be able to distribute and solve accordingly. So that becomes 2 minus 2 sine squared theta plus sine theta is equal to 2. And this is nothing but a good old quadratic. It's just in terms of sine instead of just like a normal x, okay? So, of course, whenever you're solving a quadratic, you want to get everything to one side. So I'm going to add over the 2 sine squared theta. I'm going to subtract the sine theta, and I'm going to subtract the 2, which gives me 0. What are the different ways to solve a quadratic?
Factor.
Thank you. Factoring. All right, can I factor here?
No. Yes.
I can factor out a sine theta, your GCF. That'll leave me with the 2 sine theta minus 1. Okay, don't forget GCF factoring before you do, the X method. Then I want to set both of my factors equal to 0. And this is where knowledge of the unit circle comes in. Where on your unit circle, between 0 and pi is sine 0. 0 and 2 pi, but since I'm only looking between 0 and pi, it's only at 0 anywhere else and at pi. Over here, if I do just a little bit of algebra, that's going to be sine theta is equal to 1/2. Where on our unit circle between 0 and pi is sine 1/2. Pi over 6.
5 pi over 6.
And 5 pi over 6. That's where that knowledge of the unit circle is going to definitely be helpful. Okay, remember, sine is your what coordinate?
Y.
Sine is your y coordinate. So you were looking for where sine was 0, which was here and here, and where sine was 1/2, which was here and here. So your answer would be all 4 of these solutions. Yep.
So when you plugged in the 1 minus sine squared theta, is cosine 2 theta the same thing as cosine squared theta?
Good question. Cosine squared theta and cosine 2 theta, no, they're different. So that's why it's important to make sure that, you know, if this is an exponent, we're going to use the Pythagorean identity. But if it was cosine 2 theta, then we're using the 3 double angle identities.
Okay.
Yes. You talking about this 0 or this?
The bottom one.
The bottom one. So remember, we have 0 pi radians and then pi radians. The ordered pair of 0 is 1, 0. And so since sine is our y coordinate, we do want 0, which is technically 0 pi radians.
Oh, why isn't it 2 pi?
Oh, because we're only going from 0 to pi.
Oh, okay.
So we always got to look at our domain when we are pulling out our angles. You guys try this one on your own. Be cautious of, you know, which trig ratio you should try to work with, your domain as well. Online, how do we start?
I
Use a trig identity.
All right, which one?
Was the one that made sine squared 1 minus cosine squared x. So you could have all cosine. And then you would distribute the 3 through it, and then it would be a quadratic once you distributed all of it and added it to.
Very good. So I distribute. This is another quadratic. Me personally, I like to work with my quadratics when that squared term is positive. So I'm going to move everything over to the right by adding over cosine, 3 cosine squared x minus 4 cosine x, and then plus 1. It was combined and moved it over to the right-hand side. It's a quadratic. Do I need to review factoring? Add this factor. Classroom.
I got cosine squared x minus 1 times 3 cosine squared x minus 1.
Now you're saying cosine squared x. Do you mean cosine squared x?
No, ma'am.
Okay, so cosine, so it's cosine x minus 1.
Yes, ma'am.
And then 3 cosine x minus 1. There we go. All right, for those who might have forgot, you know, California, you multiply A and C together. So you're looking for, oh, works now? Nice. So you're looking for 2 numbers that multiply to give you 3, add together to give you -4. That is 3 and -3 and -1. So you know we would write it, but then we have to slide divide bottoms up. So we divide by 3, and that's how we end up with cosine x minus 1 and 3 cosine x minus 1. So that means that cosine x is going to equal 1 and cosine x is going to equal 1/3. Where on the unit circle does cosine x equal 1? 0? Anywhere else?
No, they're not.
No, that's it? Okay. And what about 1/3? No place on the unit circle where cosine x equal or cosine equals 1/3? Yes, no, maybe? No? Very good. It's only 1/2 √3/2, 1 and 0. Okay. So in this particular case, if this were a non-calculator question, which I had you guys do it, you wouldn't be able to provide a solution here. However, go ahead and pull out your calculator. Since I am looking for an angle, I need to do what? I need to do the inverse. And be very careful. What mode do I need to be in? I need to be in degree. And the only reason why I need to be in degree is because of this right here. It said that x is in between 0 and 90 degrees. So when I do the cosine inverse, I want to make sure I'm in degree mode. So then the calculator knows to provide me with a degree, not a radian. So let's double check that real quick. My mode is on degree. And then I just do cosine inverse 1 divided by 3. And then this will be the other angle that I need. And it is between 0 and 90. So round at the three significant figures, x is equal to?
75.
Very good. That's also how we can do it in our calculators as well. Of course, just double check that domain so I know if I'm doing it in my calculator, whether I need to be in degrees or in radians. All right, I think we'll have time to do one more. I'll save that one where we are just the bounds for tomorrow's or Friday's class. Okay, let's do this last one together. Solve 2 cosine squared theta equals sine 2 theta. Okay. I haven't heard from a few of you all. So if you haven't talked today, help me out and tell me how I can start this problem to solve it. So you want me to call you out?
I just have a question.
Question, perfect.
So for the sine 2 theta, that's different from if the sine or if the 2 is in front of the sine, correct?
Correct.
Okay,
Yeah.
thank you.
Don't have me call you out.
Would you need to use identities to change both sides?
Depends on which route you're trying to go. I mean, you're definitely going to need to use identities for sure, but depending on which identities you use, you might not need to change both sides.
Using one of the double angled ones, couldn't you change the sine 2 theta to 1 minus 2 sine squared theta?
You are mixing cosine double angles with sine double angles.
Oh, okay, I see it now. Never mind.
The sine double angle can change sine 2 theta into 2 sine theta cosine theta.
I can change that. What?
Yeah. Because it seems like there's extra steps. Does that work?
I mean, both ways work. But the question is, where would you go from here? Either side you chose. Okay, yes, that. I know that. But I mean, after this, where would I go? After I distribute on this side, what would I do from there?
Oh, wait, because it's got the 2, and so that's what it, oh, no. I don't know what you do for that.
This right here, that's a double angle. It's not like a exponent. That two is not an exponent, so I can't use a Pythagorean identity with this one. I am going to need to change that using the identity. So I mean, you can change both sides. You could.
Oh, so with the other one, though, if you divide 2 cosine over, you get cosine theta equals sine theta, right? Or you cannot do that.
Well, I'm glad you said that because I didn't want to highlight this. You said divide
Yeah,
both sides by cosine?
by 2 cosine.
By 2 cosine. Now, when I divide by,
Then you get cosine theta equals sine theta. And then that would be,
What?
and then in radians, that would be pi over 4 and 3 pi over 4.
I think I need to write down what you're
Oh,
saying.
I see what you're saying.
Because it'd be the root
Oh,
over 2.
yeah, yeah.
So then it would be,
You're saying do this?
yeah, then it would be pi over 4.
Hmm.
That would be in the square root of 2 over 2 and square root of 2.
So you're saying here, you're looking for where the sine and cosine are equal, and since we're between 0 and pi, you're saying pi over 4, and that's your solution?
Yeah.
But didn't we get rid of the solution when we got rid of that cosine?
Yes. When you divide by a trig function, you're losing a potential set of solutions by dividing by that cosine. So this is one of the solutions, but there's one more solution that you've missed by dividing out a trig function. So if you recall from long time ago, a year ago, you don't want to divide because you end up losing a set of solutions. You want to do what instead of dividing?
Factor out.
Factor.
You want to factor out
Oh.
because then you can set both factors equal to 0. So let's back it up just a little bit. Pi over 4 is a solution. Yes, it is a solution, but you lose a solution by dividing. So instead, bring everything to one side. And then factor out that cosine instead of dividing. And I can even factor out a 2 cosine. Because then when you're left with that cosine theta minus sine theta, you still get that set of solutions when you set the inside equal to 0. There's that set of solutions that you had before, but now you also have this one as well. Okay, so yes, theta is still pi over 4, but it is also
Pi over 2.
pi over 2. Okay, you would get the same thing if you did it over here, changing both sides. You just want to make sure that you replace this double angle identity as well. And then, actually, no. No, don't do this row.
So you just have to kind of fiddle with it until you.
Well, I would say if anything, if you have a double angle identity, replace that for sure. And then see if you can work with that alone and then kind of hold off on using the Pythagorean identity if a double angle is involved. Okay. Well, we'll stop it there for today. Just make sure to recap a few things. Make sure you know you're in a circle, apply your identities, and make sure you're also aware of what quadrant you need to be in when you have like these types of problems. Okay.
What would be an example for if you're in the third?
Ooh, you're more likely if you're in the third quadrant to see a problem like this and then adjusting the domain here.
Okay, but it's not gonna have anything about like.
Obtuse or anything like that.